All right, I would like to welcome Jay Kim, who will be presenting his talk on anomaly detection using various AI techniques. At Magnimind, we strive to find speakers who can deliver talks like these filled with current information and fresh perspectives to go along with our data science education programs. These programs are designed to build the fundamental knowledge needed for a career in data science, and we aim to impact the careers of as many people as we can. Whether it's refining the skills with our mini boot camps or starting an entire change with this with the support of our mentors, Magnimind has something to offer for anyone. Any experienced data scientist knows that anomalies, outliers, errors, they happen all the time, and especially during testing. But if left unfixed, they can throw off an entire system. And our talk yesterday was focused on the future of AI, and now we'll take a step further and showcase one of our many implementations of how AI can be used in data science. Jay's talk will show us the future of detecting anomalies and how they can be fixed automatically, which could potentially save hours of time, especially with business. Without further ado, here is Jay Kim.
Welcome everyone. Thank you for coming today. Can you hear me okay? Okay, so yeah.
Yeah, we can hear you.
Okay, thanks. So yeah, I want to talk about today about the anomaly detection using various AI techniques. I have been working as a data scientist for a long time, and also many of the use cases we have to detect the anomalies very often times. Many difficult problems actually is involved with the anomalies. But detecting anomaly is not that easy. There are a lot of the situations is going on, and we have to understand what kind of business cases and also the situations. And also not only the understanding, but also we need a lot of the various techniques to detect correctly and also accurately. So today I want to introduce you some very typical and also important AI techniques to detect the anomalies. So today I will talk about the introduction first, and then the applications, and what kind of things we want to actually detect, what can be actually anomaly, and then finally I will talk about the techniques. I will talk about some technical stuff here, so it might be a little bit boring, but I try to make it more easier. And then I will give some examples about the use cases, and we will finish this talk here. So before we start, this is me. So I have several like some experiences, and now I'm working in the so-called case as a senior data scientist, and I'm doing some internal consulting as well. Also, there are a lot of the project is going on, and right now I'm working on two big projects, and then it's actually in production stage right now. So one of the project is actually anomaly detection, so which is really difficult. But with the neural network model, actually, I could be able to manage to detect those anomalies. So yeah, I will talk about that later a little bit, the techniques. So what is the anomaly detection? Actually, the anomaly, and before we start, actually, we need to understand what is the anomalies and what is the outlier. So it's very similar term, but it's actually very different. So outlier can be anything which is abnormal, but the anomaly is kind of something is valuable. Something is actually valuable for business, or some like kind of some the work. So the so kind of anomaly, you can think anomaly is a subset of the outlier, but it's actually more meaningful stuff than outliers. So yeah, this is actually definition of the outlier and anomalies. So outlier can be anything, which can be actually including the noise. But the anomaly is a kind of very meaningful outlier, which can be good information and which can be actually used in different businesses and analysis. So more specifically about outliers. So most outliers actually can be actually scored. So significant, we can actually score with the statistics and also some probabilities. And there are many ways of the score. And then also we can actually label as the outlier as the labels. So we'll talk about that later with the more examples. So what can be used for anomaly detection? So there are many applications for anomaly detection. So actually fraud detection is actually most common application from the anomaly detection, right? So we can actually detect the fraud, credit card fraud. Someone actually can do some fraud in the online or the phone call. The AI can actually detect it, and then we can actually we can check the behavior of the some kind of fraud calling behaviors, and then automatically by AI. And then there are many medical practice kind of those kinds of stuff can be actually detected as well. And then there are many different applications like that. There also another common application is the e-commerce. So pricing issues and networking issues actually can be detected. So and also intrusion detection in the security. Actually, some people try to hack some people's computer, but the behavior is very different from normal behavior, right? So the AI program can actually detect it. And also in the medical anomaly, so some kind of cancer detection, right? Some people have cancers, but the image of the cancer is different from normal people. So from the image, they can actually detect the anomalies. And also manufacturing and also sensors. So in the IoT, we can actually detect the different phenomena. So force detection and heat fire sensors. You can detect the high heat or fires. And also in the text analytics, you can detect the different behavior like plagiarism, right? The novel topics, which is different from normal text. So those can be actually used with the AI. And then also, so the aspect of the anomaly detection is actually it's very important for, I mean, many different applications, right? The anomaly is actually the main thing we have to detect. So there are many ways to do that. So yeah, I will talk about the techniques and what kind of the aspect we need. So before we actually find out the anomaly, we need to know what is the main signal and what is not main signal, right? So defining the normal signal is very important. So what can be actually normal signal, normal distribution, and then which is not the normal like something we don't want or outside of the what we have, like some main signal. So so for that, there are many different techniques like a clustering or K nearest neighbor, those kinds of stuff. So I will talk about that later more. And then, yeah, I a little bit talk about it earlier. Why it's important? Why defining the normal signal is important, because if you define wrongly the normal signal, then that means we will actually we will find the outlier or anomaly in wrong way. So actually it's wrong from the beginning. So we have to actually find out the normal signal in the beginning, right? So to do that, we need to actually see the statistics like the z-score or normal distribution or like p-value. We have to see the distribution, and then we have to know that what is actually main signal and what we are actually looking for. So this so this score is one of the popular score way, and also Gaussian distribution. Another term is normal distribution. So we can actually see that what is actually normal signals that we are actually having main signal, and then also what can be actually outliers. Yes, this is just an example. So you can see the normal distribution in the left picture. So most of the signals are in the middle, in the outlier maybe in the side, left side and right side. In the second case, it's not normal distribution. So this one cannot be think that way. Right? And then another way, so in the left side, main signal is actually in the line regression, right? And then the outlier can be like far away from the line. Another term is a model, right? It's a linear model. So it's more far away from the linear. We can actually think as a kind of outlier or anomaly. The left side is a kind of clustering model, and we can see main signals are in the it's a clustered, but the outlier or anomaly can be maybe spread out. So we can see from the some modeling perspective as well, like this. Yeah, so it's very challenging because if the signal is very clear like this, then no problem. But most of the cases, the signal is not clear enough. So there are many different cases, and also a lot of the different dependencies and many different like the noise is actually included. So getting really good anomaly is not really easy. So we have to think about many different problems. And so whenever you actually dealing with the anomaly problems, it's not, you have to actually define the problems first, and then also you have to think about the different dependencies, and then we can actually go to the actual problems from there. But it's not easy, as you can see. So another way to actually detect the anomaly is classification. I think everyone knows about classification, but problem of the classification is that we need enough labels. So without label, we cannot do actually classify. But there's another way. Actually, we can actually classify without labels, but there's a more advanced technique, something like semi-supervised learning or active learning, which actually doesn't require enough labels. But normally, actually, we need labels to the classification. So for that, the anomaly is not happening very often. So the getting label is not very easy. Yes, but it's possible. So I will talk about what kind of the techniques can be applied with the classification here. So point anomalies and contextual anomalies and collective anomalies. Yeah, I will talk about that in the next slide. So you can see that point anomalies. Yeah, so we can actually point everything like in the 2 dimension, but it can be actually 3 dimension or different dimensions as well. But you can see some points are actually out of the main main plot, right? So we might maybe suspect some of the like some points as anomalies, and then we can actually go deep to that point, and we can analyze it if there's really anomalies or not. And then these conceptual anomalies. So you can see, we can also plot this one as a 2-dimension, but time is going farther, but it's a pattern is very similar, right? But there's some contact is not same as the other patterns. So we may be this one maybe because of the anomaly, or we can doubt of it, and then we can actually go in there and analyze this a really anomaly or not. So another example, this is in medicine. You can see every pattern is actually similar by time, but there's some peaks which is a little bit faster coming out than the other patterns. So maybe this one might be anomaly as well. But we can actually doubt it, but it's not actually clearly we can conclude it, because sometimes it can be affected by some other factors. So so we can doubt it, and then we can go more deeper analysis. But it's not, we can actually conclude that this one is clearly anomaly. Yeah, so I actually summarized some the anomaly detection techniques from 1 to 6. So 1 is the extreme value analysis. So some value is very different from, just a few values are very different from main values. Then maybe there can be actually anomalies. And also secondly, I introduced a little bit earlier, classification can be actually help. And thirdly, we can actually do some statistics. Maybe we can use some statistics to detect the anomalies. There are many techniques, so I will actually talk about that a little bit later. And proximity-based models, so clustering model or nearest neighbor model, you can actually detect it, the anomalies. In information theoretical model, something like a p-value. P-value is a 0.0, I mean, the 5% out of the all the distribution, the values. We can say it's a significant or not. Those kind of stuff. So there are many different statistics which can be used for outlier detection, and also meta algorithms and ensemble techniques. Something like sequential ensembles or independent ensembles. So this one is based on the time, but this one is not. Something like the random forest or XGBoost, they can be actually detect some way we can actually detect the anomalies. So yeah, let's start with the extreme value analysis. So the anomaly can be extreme values, so very different from all main signals. So to detect that, we can actually use some graph or can some tests with the Z-score or graph testing some box plot, something like that. So one example, so box plot. So main signals are mostly in near the mean value, and then after quarter, and then this max value, and this is a minimum value. But the outlier is actually out of the max and minimum value. So this we can actually doubt as a outlier, but the outlier doesn't mean it's an anomaly. So we have to think about what can be good for the business. So we have to analyze more to verify this is a real anomaly or not, or or it can be actually noise. So we have to be careful on choosing this one as anomaly or the outlier. Yeah, so this is another example. So this is this plot is only one variables, but this one you can see that several variables, several features can be actually we can detect the several features, the outliers each, and then we can actually verify those anomaly or not. And then 2-dimension, same thing. Main signals actually stick together, and then the outlier or anomaly can be actually out of the main signals. So we can actually doubt that it's an anomaly, but again, we have to be careful. This is whether we will choose this one as an anomaly or outlier, right? And then QQ plot is a little bit different. So you can see that it's a normal theoretical quantile. So that means it's a normal distribution, and then this is but this is a theoretical. So it's a kind of we choose a normal distribution, closest normal distribution, and then this y-axis is actual value. So we plot that as a x-axis and y-axis, and plot it. And then if some point is actually out of the main line, that means that can be actually outlier as well. Yeah, but again, the anomaly is a little bit different, so we have to be careful. If we think there's an anomaly, we have to go more further. Then classification, I explained earlier a little bit. So there are many different ways of the classification, right? So rule basis, typically the decision trees, and neural network. Nowadays it's very popular. Many actually companies or work project, neural network is more like very accurate in some way, but it has to have enough data and also compute power, right? Then SVM is another way. So it's using corner trick, and yeah, we using corner trick, and yeah, with that we can actually classify this is a outlier or not, right? In statistical techniques, is a little bit different topic, but the machine learning is kind of a statistics as well, right? So, but statistically, we can actually score in different ways as well. So, yeah, there are many different ways. So, chi-square test is a very typical way to check the significance of the data, and graph test is similar. And then I was mentioning about the box plot, yeah, which is a more think about the Gaussian distribution, and then you can see the side as an outlier. Yeah, so this is another example. So I think everyone knows the chi-square test. So we want to see the which is significant or not, right? So we can actually check the p-value, and it's less than 0.05, then it's very significant. But if it's not, then it's actually not significant. So we know what is actually more significant or not. If it's not significant, it's the more main values. Also, variance count and population variance can be actually used. And then, yeah, I was explained that a little bit earlier. Regression can be another way. So the outlier or anomaly is out of the lines, It can be actually a linear regression or non-linear regression, depending on the what kind of the model we are using based on the actual data. So the residual actually is a more higher residual. We can think as a more outlier. And the mixture model is a little bit different concept. So Gaussian mixture model is actually checking all the Gaussian without the actual value, actual data, we actually matching with all the Gaussian. For example, if there's many different features, let's say 5 features, we actually make the 5 Gaussian distribution matching, and then we try to map with the actual value with the actual variables with the different Gaussians. And if some data point is not fit to the model, then that means it can be outlier, right? So yeah, and then also autoencoder is another thing we are very popularly actually used nowadays. So autoencoder is a type of the neural network. So the X in the beginning, the X layer, first layer, is the actual data, and then in the middle layer we call the Z value, which is the compressed representation of the data. So it's actually is 4 node, and then the middle part is a 2 node. That means it's a compressing the data to latent. We call it latent space, and then after that, we the data is going back to normal. So this is generating the data back to the output. So we call this one as generated the data, which is the approximation of the actual original data. So, and then also in the latent space, we can actually check the different way of the approximation. So this kind of the, and then we can see the representation of the in the middle layer. If some value is not is close to the main value, I mean we can doubt that as a outlier as well. So there are different way of the application for this model. But yeah, I will just explain very briefly here. The proximity-based technique is similar. So if it's close enough, then that means it's close enough to the main value. Then this main data set, but it's out of the main data point, and it's far away. Then this outlier or anomaly. So yeah, this one explained very easy. So some data are out of the main point. So you can see it's not really main data, but we can doubt as some outlier. And also density can use a density of the data point. So data point are in very dense, then it's a main signal, but it's very sparse. We might think as maybe outlier. So yeah, but yeah, again, anomaly can be a little bit different. So we have to analyze more further. Yeah, and then this one the time I think I already explained this one already, right? So I'll go over. Yeah, so the time series, you can see that some value is very out of the main the plot, right? So this one might be we can think maybe anomaly because it's a very it's higher peak, much higher peak than any other peaks in the pattern. So yeah, So maybe you can think that one as a anomaly. But again, but this one can be something else. So we have to be careful. And another one is called the principal component analysis. It's called the PCA. So it's very similar to autoencoder, but this one is not the deep learning model. It's not the neural network. But you can see that the PCA is kind of checking everything in so the linear. We actually put the linear and then try to get the distance between the data point and the linear, and we actually convert that correlation to the uncorrelated variables. It's called the principal component. And then with that value, we can actually plot in the 2-dimension or two dimension from the many different the features. So for example, like from the 100 dimension to maybe you can to the PCA to 2-dimension or 3-dimension. Yeah. But we can actually choose it. So we actually get the information factors, information values from the many different the features, and then we can choose the 2-dimension because the two dimension two features has the most of the information. So we can actually cut it off, and then we can just plot it in 2-dimension and see how the each features the cross each other kind of. So we can see that like some clustering or like some which features are close to which feature in 2-dimension. So it is used for the dimension reduction. But so it's similar to the clustering method because we reduce the dimension to 2-dimension from the many dimensions, and then you can see that if some data point are far away from the main data point, then that means we can doubt that as an outlier as well. So it's a kind of technique for dimension reduction. And then we saw that earlier before, the autoencoder can be used as a principal component analysis as well, because in the middle layer, we can plot it in reduced dimension, the compressed zone. So those can be a similar application as the PCA. So yeah, as conclusion, so anomaly detection can be helping many different businesses and can solve many different problems. And the AI techniques is really useful to solve those kind of problems. With a manual way, it's very hard to actually detect those kind of things. But with the AI, you can automate it. And there are many different approaches in AI. So if you know what kind of techniques you can use in what kind of situation, then maybe we can actually do really good job. So I think knowing the what technologies are available, I think that is very important for solving this kind of problems. Okay, so this is the end of the talk. So any questions in the audience? Then I will take out the questions. Okay, one person actually asked some question. What do the top and bottom bars in the box plot indicate? If they are max and min value, why would anomaly be outside the range? Okay, so I think it's asking about the box plot, right? Okay, I will share the screen again. Okay, I think the question was this one, right? So box plot has like some max and minimum value, and then the outlier like here. So okay, and then this is a minimum value, and it's the first quarter, and this is the last quarter actually. So that means third, 3/4, and then after this or so after that is the max, and so we can actually say that it's max, and then this is a minimum. Means here like the third 3/4 of the data is over here, and then very few are actually out of the box, out of the min and max. So we can see, we can actually doubt this our anomaly, but it's a clearly outlier. And then another question: are there multiple different algorithms for principal component analysis, or just one? Okay, it's a good question. There are many different. So PCA is just a general term, but there are different. We can actually apply the PCA to many different ways. So, for example, yeah. So there are many different researches going on. So, but PCA, there's some commercial PCA that we can use as a library. But in the research, we actually develop more our own the algorithms. So upgrade more specific usage. So yeah, it's not only one. There are many different algorithms you can actually use it, or create it, or develop it. So there are many different ways. Then another question: in regression-based outlier detection, as the outliers are minority label here, what are the technique to oversample the minority level, like the SMOT, which can be good prediction rate? Okay, it's good. Yes, good question as well. So yes, so in the regression, not actually regression, but the classification. I think in my experience, classification need a lot of the label, and then the anomaly has very few, and then non-anomaly is really a lot of data. So the imbalanced problem is more in classification problem. So in the case, yeah, it's good way to actually oversample, or downsample, or doing some smart stuff like some synthetic sampling. But you have to be very careful, because if you downsample too much, then you can actually we throw away really meaningful data. Then it's not good. And also, when you oversample, if you do too much oversampling, then the data we are actually using same data again and again. That means we are over simplifying, you know. So and then synthetic is another way, which is actually we create the similar data, but it's not same. Yeah, so they can be actually help, but we have to see what is actually more, what we can actually gain more, what we don't gain more. Also, it depends. But I think the synthetic way, like smart, can be actually, in my experience, it help a lot. But nowadays there's some more techniques coming up, like the data augmentation. Right? You can actually create some fake image, but it's not very similar to what you have. We just change the angles, or we just make some little bit more specific stuff in the image, and then we when you train, it's not, and also we actually make the like a little bit smaller, make it bigger. So we actually create some make the more, create the more images, more data, more label data, right? And then you can train that way. So there are many ways actually applied. And also autoencoder, or I was working on the variation autoencoder. You can actually generate some data out of the neural network. The data can be used for label data as well. So there are many ways. Okay, another question. When do you determine the outlier is anomaly? Is there a situation that the outlier may not be anomaly? Yes, so it's a good question. In the business, there are many, we can actually detect the outlier very easy, right? Some signals are out of the main signal, but this is not always the anomaly. So when I'm working now, after I detect the outlier, I have a meeting with the business people, and then we compare. I show them what is the outlier looks, and they actually verify. They can be actually anomaly because they know like what is the value of the company, what is the business. So they can tell this is useless, or this can be actually something they can use for their business. So it's very important that talking with the business folks, so they and we actually communicate, and then they can actually give the feedback, and also if you find some good anomalies, then they can actually use it their way in their business. Okay, so another question, following up question. Sorry. Okay, does oversampling always work? Otherwise, what other technique do we have? Okay, yeah, I think I already explained, right? So not always oversampling. Oversampling is not always working. So depending on the situation, we have to use undersampling or oversampling, or synthetic way, or data augmentation. There are many different ways. So it depends. So we have to see like what kind of problems we are actually having. So from my experience, don't oversample too much. So maybe 1/3 of the data, maybe it's okay, but more than half, then it's already you're already too much generalizing your data. So you have to be careful if you do oversampling too much. So yeah, so be careful. I did not understand your explanation of the top of the bottom bars of the box plot. If the top bar and top box is 1/4 of the data and top of the box median line, and 1/4 of the data are so on for the bottom half, then that's 4 multiplied by okay. So nothing would be considered on anomaly. Okay, yeah, I don't. Okay, I think okay. I don't actually get this question very quietly, but let me see. So this bottom, yeah. So the max value is 1. Okay, 1/4 of the data is actually top, and then one. Okay, from the median, right? Median, and then 1/4 of the all the data here, and then yeah, it's a quarter, and then this third quarter, and then this is actually out of the debt. And this one is same thing. It's a median, the 1/4, and then okay, it's quarter, and then this is the third quarter, and then bottom is actually out of there. So our anomaly will be, it's not anomaly but outlier, will be out of this mean and max value. So you can think that way. Okay, so another question. Could you explain more about PCA being used along with the p-value for outlier detection? how does dimension reduction help? Okay, I think the PCA is not you cannot. I mean, you can use the p value with the PCA together, but more commonly you can use it as a clustering method. So just reduce the dimension to two dimension, and then you can actually cluster it in that dimension, right? So some value will be out of the main signals. So you can think that way. Maybe you can detect the outlier that way. The p-value, yeah, is more for distribution. Yeah, you can actually, yeah. So yeah, it's a little bit different. Yeah. Okay. So any other questions? Okay. Yeah. Thanks. So
I
I
think
think
we, hello, this
yeah.
is April. I
Okay.
think we got all the questions. And I would like to say thank you for your time and this great presentation. And thank you everyone for joining us today. You can find the record of the session in Magnimind's YouTube channel, and don't forget to subscribe our channel. And we will talk about data science through a design thinking lens tomorrow, and hope to meet you again for next events. Thank you.
Thank you very much. Thanks.